Artin has a very nice exercise where he shows you what the subgroups are of the additive group of the integers. Let's do that. Sometimes it's possible in a group, very rarely, but sometimes it's possible to identify all the subgroups. So here's a proposition I'll prove for you. Proposition. The collection, the subgroups of the integers under addition, that's an abelian group, are precisely given by BZ, all multiples of a fixed integer under addition. So all even integers, or all integers divisible by 3, or all integers divisible by 5. So we're going to check that that forms a subgroup, and then we're going to prove that every subgroup has that form. By the way, I should have said in the definition of a subgroup, a mathematician gives you a definition, he should always follow it by the trivial examples, right? Sometimes there are no more examples. Then it was a stupid definition. So who can give me two completely trivial subgroups of any group? Yeah.
The identity group and the
Perfect. So anytime you have a group, it forms a subgroup of itself. You didn't really need the notation to tell you that, but it's serially closed under addition, identity, etc. And that's the biggest subgroup you can have. And the smallest subgroup you can have is when you have just the identity element, because it must contain the identity element. And then the subgroup is like the group with one element, closed under integer. Okay? So you always have those two subgroups. Now, where are those two subgroups here? Which subgroup here is the identity element, and which subgroup is the full group? Yeah, let's follow up. Go ahead. Good. Good. B equals 0 gives the group 0 under addition, which is just the one element group. And B equal 1 gives H equal G, because if you just take multiples of 1. But the others are non-trivial subgroups. Even integers, integers divisible by 3, integers divisible by 17, integers divisible by 21. Okay, proof. First, these are all subgroups. That's more or less clear. If you add two integers divisible by b, that's just things like this. m plus bn is equal to b times m plus n. Right? The negative of bm is b times minus m. And 0 is equal to 0 times, is equal to b times 0. So that shows that the 0 element is in the group. This shows that we have inverses in the group. And this shows that the group is closed under addition. Okay? So anything, all integers divisible by something, give a subgroup of all integers under addition. We just have to show that these are the only possible subgroups. So to show that these are the only possible ones, we're going to use a trick that goes back to book 5 in Euclid. So to show these exhaust the subgroups, let H be a subgroup of Z, and let B be equal to the smallest integer. Well, there are two cases. Case 1, H is equal to 0. So it's the 0 subgroup. Well, that's one of these cases with b equals 0. So that's OK. In case 2, H is not equal to the 0 group. So it contains something other than the identity in it. Now, by taking inverses, we see that it has to contain something positive in it. So contains an m not equal to 0. Taking m or minus m in H, we see it contains some integer m which is strictly greater than 0, because it's closed under inverses. So if you found it contained -3, it would also have to contain 3. Okay, and then the trick of the Euclidean algorithm is to let b be the smallest possible integer, b greater than 0, be the smallest positive integer contained in H. So since it contains positive integers, it contains the smallest one. Okay? Then the first observation is then H contains all multiples of b. Because once it has b in it, it has b plus b, which is 2b, and then it has b plus b plus b, which is 3b, right? And then it has minus b, which is the inverse of b. And then it has minus 2b, which is the inverse of 2b. Everyone agree to that? So once we find the smallest positive integer in it, it has to contain all multiples of this by closure under addition and inversion. Now suppose there was something else in H. Suppose H is in H. And write H as some multiple of b plus a remainder term with 0 less than or equal to r less than b. We can do that by the Euclidean algorithm. You can always subtract off some multiple of b from your integer that's in the group that makes the remainder less than b. If you think of the elements in the group on the real line, here's 0. Here's our smallest element, b, which is in H. Here's some other element, h, which is in H. We just go marching off here in multiples of b until H is squeezed between two multiples of b, which means that if we subtract that multiple of b from H, the remainder is less than b. Okay? Now, I claim that r is equal to 0. Which will show that H is actually a multiple of b, so that this exhausts the subgroup. And the proof is, if not, why? Because r is actually an element in H. B is in H, so the multiple of b is in H. H is in H, so if I take H and I add to it the inverse of this, I get something in H. H plus minus mb is in H, by the fact that H is closed under inversion and addition. But H plus minus mb is r. R was assumed to be a positive number less than b. B was assumed to be the smallest positive number in H. So the only way this can be the case is if the remainder is 0. So, and r is less than b, so r is equal to 0, which says that everything in H is a multiple of b. So this is a nice application of the Euclidean algorithm, which is used to prove the existence of greatest common divisors and unique prime factorization in Euclid. But it also establishes, and shows you a slightly more sophisticated algebraic fact, that it allows you to identify all subgroups of Z with the multiples of a fixed number. And any multiple of a fixed number gives you a subgroup. Good? So there are an infinite number of subgroups of Z, and there they are.